This video covers the solutions to problem 2 of the midterm exam 2. The problem 2 is on a converter that is a small variant of the well-known forward converter that we studied in detail. The main difference between the converter given here and the traditional forward converter is in the reset mechanism. In the conventional forward converter, there is a reset winding, and that is connected to the input source with the dot polarity as shown. Whereas in the converter shown, the reset winding is connected. These terminals, instead of being connected to the input terminals, they are connected to the output terminals, meaning the magnetizing energy, instead of being fed back to the source, is now fed back to the load directly. So you would expect that the main difference in the operation will be in the reset related in the reset winding and the related process. So we are also given the load resistance, the two inductances, the filter inductor at the output and the magnetizing inductance referred to the primary side. As I saw students make mistake in using the wrong inductance. The magnetizing inductance is the larger value, 375 microhenry, and the filter inductance is the smaller one, 10 microhenry. Switching frequency 200 kilohertz, and the operating duty ratio is also given, D of 0.3. Things we need to calculate several waveforms, but the first one is the output voltage itself. So let's do that first. So this is still a forward converter, especially when you try to calculate the output voltages. So we can draw the waveform of Vrect to calculate the output voltage. So let's do that first. This is Vrect, and we can still write it as the scale is T over Ts, the time axis scale. D is 0.3 and 200 kilohertz is switching frequency. So this would be the 0.3 mark, and this is 1. Okay. So during the on interval, during the DTS period, the Vrect voltage is V secondary, which is nothing but N times the input voltage. So given the turns ratios here, N, which we normally define as N secondary over N primary. N primary is 1, so this is simply N secondary of 0.2. So this voltage here would be, and then remains 0 during the entire 1 minus DTS period. So Vrect is 0.2 times 200, or 40 volts. Okay. And Vrect average would be this 40 only for a duration of 0.3, so that is 12 volts. So from the output side, looking at Vrect is connected to the output just through the inductance, and VL average is 0 in DC steady state. Okay, only the average is 0, so that gives us Vrect average to be just the output voltage VO, which is 12 volts. Okay, that is the answer to part A of the problem. So we'll definitely need to know what the load current flowing into this load resistance as well. So that would be I out. So we can go ahead and calculate that. I out is V out over the resistance, or 12 over our load is given as 0.3 ohms. Okay, so that is 40 amperes is the load current. Okay, so one thing that will be quite different from the forward converter, which I was hoping at least many students would catch and then draw the waveforms considering that, and that is the connection of the reset diode, and therefore the reset current flowing into this node. Okay, So that is not going to change the output voltage as calculated by this one, right? Because no matter what is connected to this node, since VL average is 0, therefore Vrect average has to be equal to Vout, regardless of what other currents get added here. So what really happens due to this I reset current is part of the load current is delivered by this average of I reset, and only the remainder is really this inductor current. So I did not really take off any point actually if that current was not considered in to subtract from the load current. So we calculated the load current to be 40 amperes. The I reset, you will see soon that I reset average is 2 amperes. So the inductor current is really 38 amps average. But if you calculated and drawn the waveform corresponding to 40 amperes inductor current, I still did not take off any points. So anyway, so this is the part A. So part B requires us to draw several waveforms, the voltage waveforms, V primary and Vrect, and we'll do that in the next slide. Okay, the first waveform to be drawn is V primary. So this is my 0.3, and call this as 1 T over Ts. Okay, on interval, no question, the main switch is on. V primary is simply 200 volts, the input voltage, and it's going to become negative. You know that this is 200 volts, here is 0. So it's going to be negative, and the negative voltage, the governing winding during the on interval was the primary winding itself, and we know that voltage is 200 volts, so we went ahead and drew that. The governing winding during the off interval number 1 would be this reset winding, because that is what gives us clearly what at least the reset winding voltage is. Reset winding voltage, if we define again with respect to or the define V reset with the positive at the dot and negative at the undotted end, then V reset during the off interval 1 would be, with the polarity assigned, it is going to be minus V out, okay? Which we know is V out is 12 volts minus 12 volts. Therefore, the primary voltage, it does not have to, or it actually will not last till the entire off interval. So we'll just draw it up to, say, an arbitrary point here, and then it becomes 0. So we still need to figure out what is this time. Okay? But we know that the magnitude during this duration is minus 12 applied to the reset winding, and they are transferring that to primary. So it will be minus 12 N primary over N reset. So that would be that's negative, minus 12 times N primary over N reset. N reset is 0.1, so it's 1 over 0.1 or 10 equals minus 120 volts. Okay, this is minus 120. Okay, call this duration as X. Okay, they're all divided by Ts, so this is 0.3. Or T over Ts here is 0.3, and T over Ts here is 1. So anyway, so we have applying volt second balance for the primary. We have 200 times 0.3 minus 120 times this X equals 0, because in the final duration, which we normally call as off interval 2, the voltage is 0, so we don't have to write that explicitly. It will be this plus 0 times a small duration, so we don't have to consider that. So that gives us the X to be 200 times 0.3 over 120, or 60 over 120, which is 0.5. Okay. So in terms of actual duration, this would be 0.5 times Ts, which Ts is really 1 over 200k or 5 microsecond. Okay, so this is actually 2.5 microsecond. If we want to write in terms of T, this is actually 0.3 times 5 or 1.5 microsecond. this x equals 0.5, so as t over ts this would be 0.8, but if you want to write in terms of the actual microsecond, this will be 0.8 times 5 or 4 microsecond here, and this duration is 2.5 microsecond. Okay, so 2.5 plus 1.5 giving you 4 microsecond, and this point would be 5 microsecond. Okay. So you can write it in either format, either actual time or as t over ts. Okay, so that is your V primary. Then the next waveform that was requested was V rect. Okay, which actually we drew in the previous slide as well. So anyway, just go ahead and draw it again, just to complete part B. Okay, this is the on interval 0.3. And for the entire off interval, both off interval 1 and 2, this is 0 volts. So this is V rect, and this one is a constant value here, is 200 times 0.2 or 40 volts, and its average we saw is VO is 12 volts. So that completes part B. Okay, so we can move on and draw the current waveforms, and the required currents are I reset, and the output filter inductor current I L out, and the input current I in. Okay. So we'll start with I reset. So that would be 0.3, and the off interval 1 lasts for a 0.5 as t over ts, so that would be, this is 0.8 and here is 1. So drawing the reset current first, I reset, it has no zero current during the entire on interval. Then it jumps, it should be drawn 0.3 here, so just jumps to some value corresponding to the peak magnetizing current in the primary, and then reaches exactly 0 at the end of the off interval 1. In fact, the off interval 1 is governed by when the reset current reaches 0 and remains 0 for the remainder of that period. Okay, so we just need to calculate this, and once we have that, we can also calculate the average. I reset average. Okay. So how do you get the peak value? So look at the primary current, magnetizing current peak value. So I am magnetizing peak. If you want to call this primary, that is okay too. I am peak in the primary. So this is just the primary inductance being applied primary voltage. Okay, so during the on interval, the voltage is 200, or it is V in dTs over L mag on the primary side, refer to the primary side. So that would be Vn is 200, D is 0.3, that is given, Ts is 5 microsecond for 200 kilohertz, and so L mag primary is 375 microhenry, resulting in I mag peak primary side of 0.8 amps. Okay, then you need to refer this to I reset peak, would be this I am peak on the primary side, times you are referring a current which has inverse relation to the voltage. So if you are referring the primary current to the reset winding, for currents it will be simply N primary over N reset. Okay. From here, N primary over N reset is 1 over 0.1 or 10. Okay. So that would be 0.8 times 10 or 8 amperes. Okay. So this magnitude that we were looking for is 8 amperes. Okay. All right, then I also need the Okay, I'm just looking where to write this. You can go ahead and write it here. So I reset average, cycle by cycle average would be basically area of this triangle divided by the total duration, which is actually just 1. So that would be area would be 1/2 times the peak, which is 8, times the base, which is 0.5. 0.8 minus 0.3, 0.5. Okay. Right, so that is 2 amperes. 4 times 0.5. So we can write that I reset average to be 2 amps. So the current that comes in, its average value is 2 amperes. So that's what I mentioned earlier. The current that goes here is 40 amps. Current that comes here is 2 amps. Therefore, the current that flows in the inductor average value is 38 amperes. All of these are average quantities, right? In particular, I reset has this wave shape, which is far from being a constant DC. But its average is what is important to calculate the inductor current. Okay, so the next current waveform that was required was the filter inductor current. So that will be positive for this application here. So this is IL in the IL out. 0.3. This probably does not matter. 1 is what matters for this. Okay, T over TS. This is 0.3. We know that its average value average is 38 amps. Okay, I just explained where I got the 38. There is the load current of 40 minus the reset current supported 2 amps. The balance is the inductor current. Okay. So it's going to have a ripple, and we need to still calculate the peak to peak value and the lowest point right at the end of that period. Right. So delta ILO. Maybe I can squeeze in that here. Okay, delta IL. Oh, this just being a forward, which is similar to a buck, has a peak to peak ripple of VO times 1 minus D TS over L. Okay. Or even if you don't consider this as a known converter, if you want to treat this as something that we're not seeing, then you can actually see the inductor voltage is minus V out during the off interval for the entire 1 minus DTS period. Therefore, the peak to peak current is the volt seconds divided by L. Volt seconds is VO, duration is DTS, 1 minus DTS. Volt second is VO 1 minus DTS divided by L is the peak to peak ripple. Okay. So that would be 12 times D is 0.3, so therefore 1 minus D is 0.7 times 5 micro, okay, divided by L, which is 10 micro. Okay. So that gives us delta ILO of 4.2 amperes. This delta ILO is 4.2. Or this peak value would be 38 plus 1/2 of 4.2. So that's 40.1. And the lower value of the current is again 38 minus 4.2 over 2, which is 35.9 amperes. Okay, so I removed a lot of ink here to make space for the final waveform, which is the input current IN, which is also a positive only waveform for this converter. Okay, this is going to be IN, and same 0.3. Not sure if you need this, but if it is 0.8, and this is going to be 1 T over TS. Okay, so IN is going to be simply I primary in this case. Okay, that is another difference between this converter versus the conventional forward, where during the reset interval also there is an input current actually in the negative direction charging the input source, but now the reset energy goes to the output, so there is no current during that entire off interval. So there's only current during this 0 to 0.3 TS duration. Okay, so that is going to be In has two parts. Is I secondary referred to the primary side, so I'll write it as I secondary times N, or N secondary over N primary, plus the IM instantaneous current. Okay. So we already saw that IM peak on the primary side was this 0.8 amperes. We calculated this to draw the reset waveform earlier. Okay, so during the at t equals 0, at t equals 0, I in or I primary equals this current here. Okay, so it's going to be 35.9 times N secondary over N primary is 0.2. Okay, so that value is 7.18 amps. And notice that the IM peak IM at t equals 0 is 0. That is why there is nothing added to this I secondary prime. Okay. Whereas at t equals 0.3 TS, we have IM is equal to the IM peak, which is 0.8 amperes. Okay. So therefore In, so at t equals 0.3 TS, In equals the ILO, which is 40.1 times the N secondary over N primary, which is 0.2. So that is 20. So that's 8.82. Not really. So not written that explicitly, but this plus the IM peak of 0.8 amperes plus 0.8, so that is the IM peak. So this whole thing, that is equal to 8.82. Right, so I will draw the final input current In. So a value only during the on interval dTs, and then 0 for the rest of all the way up to 1. Okay, this value was 7.18, and this value that includes the magnetizing current peak is 8.82, to give an average. Okay, In average, you can get that by doing the 7.18 plus 8.82 over 2 times 0.3. That would be 2.4 amperes. Okay. So you can also verify that Bin times the In average should be equal to 200 times 2.4. Should be equal to the output power, which is output voltage of 12 amperes times an output current of 40 amps. Okay. So it should come out to be they are exactly the same. Okay. Okay, so that is the entire input current waveform, and what we are left with is the final part D, which is calculating the voltage rating of the switches. What we need is the voltage rating for S1. S1 is the primary side MOSFET. So let's see if I have deleted the V primary waveform. Okay, here is the V primary waveform. So when you want the voltage of S1, you consider when it is off, and that is this interval here. Okay. So this end is always at 200 volts with respect to the ground. So the switch voltage would be 200 plus whatever is induced voltage. So during the off interval, the induced voltage with this side is positive, or if you just retain the assigned voltage polarity, the voltage is actually 120 at the bottom with respect to the top. So the total voltage across S1 is 200 plus the induced voltage of 120. Okay. So that gives us the voltage rating of S1 to be 200 plus 120, or 320 volts. Okay, then voltage rating of the diode D1, this diode here, D1. Okay, so D1 supports or blocks a voltage when this diode, reset diode, the freewheeling diode is conducting, and when that happens, the voltage across the D1 is simply V secondary, and we're looking at the V secondary during this off interval 1. So that would be so the governing winding during that off interval 1 is the reset winding, which has a voltage of V out, right? So the voltage rating for D1 is V secondary during that interval. So that would be N secondary over N reset, which is the governing winding, and the applied voltage to reset winding is V out, which we calculated was 12 volts. Okay, so that would be 12 times N secondary over N reset would be N secondary is the one which is 0.2. So it's 0.2 over 0.1, or 24 volts. That is the voltage rating for the diode D1. Okay, so I think that completes the entire problem 2.